Okay.
All right. Good morning, everyone. It is just after 10 a.m. here Eastern Time in Kentucky. So welcome to our next AP Calculus AP Content Review session. My name is Aaron Timmons. I'm the Math Content Director for Advanced Kentucky. We are fortunate today to be joined by Virge Cornelius. You all probably recognize the name without an introduction, but Virge will go over her credentials here shortly, but I'm going to take just a few minutes here to go over some intro slides for us. While we're getting situated, please make sure you got today's handouts at the bit.ly link there on the screen. All right, so this online review session is intended for a Kentucky audience, but I know we have lots of people from around the country, so welcome. We'll do everything we can to make this as engaging as possible. If you are causing a disruption, however, you will be removed. And AP is a trademark registered by the College Board, which is not affiliated with and does not endorse this product. Advanced Kentucky is happy to host today. Our Twitter, Facebook page info is right there, along with my email on Twitter. Please give us a follow. Give us a tweet on Twitter. Virge is also on Twitter, so you can tag her.
Yeah, but I'm terrible at Twitter, actually. I'm better at Instagram if anyone wants to find me there.
Your microphones and video are off and disabled for this session, but your chat is enabled. So please communicate through the chat. You can chat directly with myself or Virge or with the entire group. We'll make sure any questions go and get addressed to all of us, as you know, especially Virge, so she can give her feedback. So please use the chat. That is the way we want to make this interactive. So all questions you have, please send them through there. And then today's recording of today's session will be posted to the bit.ly link where you all registered. You can also find information for future review sessions, as well as recordings and handouts for all past review sessions. And this applies to all AP Math, Science, English, Computer Science courses. So you may be here today because you are an AP Calculus student, but if you are also taking AP Biology or AP Seminar, you can go to that website and get links for those sessions as well. So those are my introductions. So without further ado, I'll turn it over to you, Virge, and you can take it away.
So, hi, everybody. I don't know if you watched on Thursday Night Live or whatever, but my internet was having problems and still having problems this morning. So now I'm in my husband's office instead of in our exterior office. And that was a quick switch at the end, but I'm happy that you guys are here. I am in Oxford, Mississippi, and we're going to do 2 hours of calculus together today, focused on integration and anti-differentiation, pretty much. So I hope you have paper and pencil with you. We're going to be doing a lot of writing together, and I am not a PowerPoint type person. I'll be doing it all on my document camera. So anything I'm writing down, you can do the same. What else should I say, Aaron?
I think that covers it. We'll
Okay.
put any links that you need in the chat again here for those of you that don't want to bounce back and forth. But again, yeah.
And I'll be slow enough that they can copy it down, honestly, without the handout if they want to print it later or something like that. So
sounds good.
Yeah. Okay, so we'll get started. Let me see if I can share my screen. And yay, did it. That's good, right? Okay, so welcome to all the students. I'm so proud of you. Calculus is it's a hard topic for sure, but it's a crucial topic in terms of advancing your education, and it's, for a lot of us, it's a really fun subject area too, on top of it all. So so welcome to everybody. You got up early, especially if you're on the West Coast. Whew, you got up really early to join us. Okay, so this is what I'm going to do today. This is what I'm going to try to do. Like I said, we're going to go ahead and we're going to work on integration and anti-differentiation. And so what that means is I want to start with the basics. Okay, we're going to start by building a sheet that you guys can reference for yourself throughout the rest of your study time, and you might even take it to college with you or into your BC calculus class next year in high school. Then I want to go ahead and do some techniques of integration, such as like U substitution and things like that, and some more advanced techniques like maybe when would you have to complete the square, things like that. Then we're going to go ahead and do a Desmos activity and take a break. Yay! We'll take a break after that. And then we'll come back and do another Desmos activity that has to do with slope fields. Mark wrote this one, actually. Mark Corrali. He's actually doing the session next week. So on, and he actually might pop in. Aaron, if Mark pops in, make sure you tell me, okay?
I will. And Mark is doing our BC session next week, but Dixie Ross is taking over for you next week.
Oh, okay, okay. But you know, they could go to the BC section, I guess, session if they wanted to, right?
Yeah, absolutely.
Okay, or watch it later. And then after that, we're going to do a little activity on differential equations. So that's kind of my idea of how we're going to spend these 2 hours together. So please, like Aaron said, if you have a question, put it in the chat, and I'll do my best to answer it. So anyway, without further ado, let's get started. I have this yellow sheet of paper, which has gotten kind of quite a reputation, actually, especially among teachers. But what I do is I give this yellow sheet of paper, which is literally just a piece of paper from a legal pad, to all of my students when we start derivatives, actually. And what I do is we build together pretty much a study sheet or a reference sheet that they can refer to all year. But of course, they can't have it on the exam, but hopefully by then it's you know, it's second nature to them. So we're going to do the same for integrals anyway, or antiderivatives. And we're going to build this together, just kind of thinking about our basics and making sure we understand what's going on with integrals. So first thing I would think of is my power functions. In other words, like if I had to do the integral of x dx, what would that become? The idea of the integral is really that you are anti-differentiating. This is the integrand, and you're trying to like find the original family of functions, okay? If it's indefinite like this one is. So what would this have been? It would have been 1/2 x squared plus some constant. Now I'm going to write a bunch of these, and then I'm going to give the generalization. And as you prepare for the AP exam, you're going to need to continue to write these sheets over and over for yourself so they become second nature to you. Another thing underneath the power functions that I would put anyway is something like the integral of 3 dx. What do you do when you see like 3 dx? Well, that is just really 3 would have been the derivative of 3x. So make sure that you recognize that, because a lot of times students will just bring the 3 over, and then they won't, if it's got limits of integration, they won't do that b minus a that they need to, and that's not good, because then they're not calculating the area that they need to. All right, what if we had something like the integral of x squared dx? Well, again, I'm going with integration and anti-differentiation. I'm going back to that original function. So I have to add 1 to my exponent, and I have to divide by that new exponent or multiply by the reciprocal. So 1/3 x cubed plus c. All right, so now we've kind of reviewed enough that maybe I make a generalization. And actually, all you really need is this rule, which I call the reverse power rule. So this is the integral of a x to the n dx. Well, that's a lot of variables, but the only variable really is the x, and I know that because of the differential. So this is a coefficient, kind of like that 3 there, and then this is an exponent. This is a power function. So I'm going to say, this would be a times, I'm leaving a little space, I got to add 1 to my exponent, and then I got to multiply by the reciprocal of that, or divide by that new exponent. So the integral of ax to the n dx ends up being a times 1 over n plus 1 x to the n plus 1 plus c. By the way, it's very weird to do this, Aaron, and nobody's like saying anything, right? So at least with Mark, when I'm recording or we're going live, actually, like we're talking to each other about it, right? So this is really the biggie right here. But I think especially when you're doing calculus for the first time, which AB students are, they kind of need to see the progression there, and I hope that's helpful. Now, still with power functions, if you have something like a square root, so the square root, so the integral of the square root of x dx, remember that's a power function. The square root of x can be rewritten as x to the 1/2. So I have the integral of x to the 1/2 dx. And what happens there is that I would add 1 to my 1/2. So 1/2 plus 1 is 3/2. So x to the 3/2. and then multiply by the reciprocal there. So 2/3 x to the 3/2. Remember, anytime you can always just go ahead and differentiate here and make sure you get back to that integrand. So 3/2 times 2/3 is 1. X to the 3/2 minus 1 is going to be 1/2. And so, yes, I did. So we also have, of course, in these power functions, they're not polynomials, of course, but they are power functions, something like 1 over x cubed dx. Now, that could be rewritten as the integral of x to the negative 3 dx. So all of our rules from algebra kind of getting us ready to do calculus. And then I would want to add 1 to the exponent. So negative 3 plus 1 is negative 2. And then divide by that new exponent or multiply by the reciprocal of it, and then plus c. So that kind of is my power functions, and you can go ahead and make your chart a little bit, or your yellow sheet a little bit better. You know, I have a student who actually takes notes on her iPad, and she's my only one, so she can like zoom in and zoom out, and she can really make nice boxes around everything and things like that. So one thing that 1 over x cubed dx, one ratio that's really important for us to know is the integral of 1 over x dx. And this, even though 1 over x dx is a power function, it's not in this family of how do I anti-differentiate it. This we need to know ends up being the natural log of x, absolute value of x plus c. So that's kind of like a little special case there. You could call it, you know, logarithmic or something like that. And then also kind of here, I'm going to put logs, ... When I think about logs, then I think about exponents. So exponential functions. And I think about the integral of e to the x dx. Well, the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x, and then plus some constant. Of course, the derivative of a constant is 0. That's why we don't see it in the integrand. One thing that came up in our work this week on YouTube is that you definitely need to be able to anti-differentiate and differentiate when the base is something other than e. It doesn't come up that much, but it comes up enough that we need to address it. So for example, if I had the integral of 5 to the x dx, this is definitely an exponential function. And so this antiderivative would be 5 to the x, but then divided by the natural log of 5, and then plus c. So on the flip side here, you could go ahead and write all of your derivative rules. And, you know, one of them would be that if you had y is equal to, and there's a lot of ways to write your derivative rules, 5 to the x, then y prime is equal to 5 to the x natural log of 5. We did that, I think, on Monday in our YouTube live. So we might want to generalize here, and we might say to ourselves, all right, what if I have the integral of a to the x dx? And again, I know that x is the exponent. I mean, x is the variable, but it's in the exponent. So this is not a power function, it's an exponential function. And so this integral would end up being a to the x divided by the natural log of a, and then plus c. Now, that's a half a page. But I had to save another half a page for what? Trig, right? We got to know our trig. So I'm going to go ahead and start with some of the trig that we need to know. So for trig, and if this were my classroom, I would say, well, what do we need to write down? So be thinking to yourself, well, what's she going to put there? So she's going to put like the integral of sine x dx. That's going to equal negative cosine of x plus c. Or the integral of cosine of x dx, that's going to equal positive sine x plus c. I remember being in high school and taking AP Calculus, and that was like in the dark ages in the 1980s. But I had to always think to myself, like, okay, the derivative of sine is cosine. The derivative of cosine is negative sine. That's why I need that negative there. So little things like that to help yourself get the SIGN, right, with these trig functions. All right, what about the integral of secant squared dx? that's going to be tangent x, and then plus c. And then we have some, you know, maybe they're not the leads in the show or anything like that, but they do occur. The integral of secant x tangent x dx, that would equal secant x plus c. The integral of cosecant squared x dx would equal negative cotangent x plus c. And then finally, the integral of this guy here. So cosecant x cotangent x dx would be negative cosecant x plus c. Now, if you have had plenty of coffee or caffeinated beverage, you're probably thinking to yourself, how come she didn't put the integral of tangent x on that list, right? Like, shouldn't I have put the integral of tangent x dx after this list? I mean, wouldn't that make sense? Well, it would, but that's a little bit more complicated, and we're going to get to that when we do our techniques of integration. These are just our basics. All right, and then one last thing, well, at least I think one last thing for now anyway, are these inverse trig. So inverse trig. And the two big ones that you need to know for inverse trig, and I'll call it a day with that, would be the integral of 1 over 1 plus x squared dx. This is going to be our inverse tangent of x plus c. And then our other one is the integral of 1 over the square root of 1 minus x squared dx. And this is going to be our inverse sine of x plus c. And both of these can be written with like arcsine of x plus c or arctangent of x plus c, just as a little reminder there. I'm leaving a little space here for some other stuff, but anyway, so those are some basics, and those are the things that hopefully you can refer to this sheet quite a bit in the next however many days. My students are taking the exam on the 4th, but you might not be taking it till May 24th or even sometime in June with that digital administration. So those are, like I said, some of the basics. So what happens after basics is that we have some different techniques of integration. So if something doesn't fall into this basic category, then we might do something called a U substitution. So a U substitution. We might have to do some division to rearrange our integrand. U substitution, we would try and rewrite our integrand. It's kind of a reverse of the chain rule. Division, we'd try and rewrite our integrand, so it's maybe got a couple pieces that we can anti-differentiate. We might even have to do something like complete the square or factor, something like that to kind of rearrange algebraically our integrand so that we can then apply one of these basics. So we're about to work on all of these things all jumbled up together because this is a review session. I'm not teaching each one of these individually. We're just reviewing it together. Okay, so in the actual Aaron, how did you send it to them? Did you send it like in a Dropbox or in a Google folder? Or
If they click the link, and I'll put it in here again, then they can go to a Google folder and download it or open it up.
Okay, so this is a set of exercises, and you might have actually already done it, you know, but I do this stuff all the time, and it makes you actually better if you do it again, because the first time you do something like this, even a teacher, to do a set of exercises like this, you're going to ask at least a couple questions, and so hopefully the next time you do it, you have to ask fewer questions until you've done it several times, and you're good, you know how to do the whole thing. But this is a circuit, and it's something that I wrote. It's mixed integration practice. So what that means is, like, I'm not just asking you to do your basics or your U substitution or things like that. Like, I'm jumbling them all together, which is where we need to be as we're getting ready for the AP exam. So what we're going to do is we're going to start in this first box, and we're going to anti-differentiate here. We're going to figure out this indefinite integral, and then we're going to search for our answer, and that's going to become the next one. I actually already worked this last night, or maybe it was this morning, I don't remember. So you can see that I have my answers here, okay? So in terms of what number it is, but in any case, we're gonna actually do the work right here together. All right, so here I have the integral of 3x squared plus cosine x dx. And remember, we can think about the integral of a sum as the sum of the integrals. You do not need to write this, but this is permissible, okay? And it's important that you realize it's permissible for addition and subtraction, but not for a product. If you have a product like this, you would have to use some different technique. So usually what I do is I just go straight ahead and I anti-differentiate this part and also this part. But I've rewritten it, so here it is. So the antiderivative of 3x squared, or an antiderivative because there's that plus constant, would be x cubed. Add 1 to my exponent, 2 plus 1 is 3, and then divide by that new exponent, and I have just a 1 for a coefficient. And then plus antiderivative of cosine x would be sine x plus c. And again, we can take the derivative of that to check and make sure that we have the right integrand. One thing is, and Mark and I have been going through tons and tons of multiple choice problems. Oftentimes you're asked to do an integral and then you have 4 choices, right? So those are really, if you would take the derivative of those 4 choices, you could get the result that you want. You know what I mean? Instead of anti-differentiating, you could look at your answers and you could differentiate. It's just a suggestion. All right, so now we're looking for that answer because that's going to become my second problem. So let's see if I can find it. Oh, here it is. Okay, so here's my second problem. So I have x cubed plus sine x plus c. That was my answer. Yay, happy about that. So this is my second problem. All right, so I have the integral of 3x squared e to the x cubed dx. This is exactly what I just said. So this is a product right here. I can't anti-differentiate each piece. That is not permissible. I have to really think about what I might be able to do, some other technique. So what I would do here is I would look at this product and I would say, this looks like somebody used chain rule and got this integrand as a result. And so what would they have maybe done? Well, this x cubed might have been that inside function on chain rule. And chain rule is hard. I get it. I mean, it is one of the hardest things to master. If you, a lot of the feedback from our lives so far has been, I need more practice on chain rule and that kind of stuff. So definitely do that for yourself. Get some more practice on chain rule. But U substitution, which is what I'm about to show you, is chain rule in reversed. So I would let U equal x cubed. Okay, that's my inside function. And then I would do du dx, take the derivative of u with respect to x and get 3x squared. Now from here, or even before I did that step, some teachers do it different ways. So don't worry if your teacher showed you a different way. There's lots of different ways to do U substitution. I'm going to go ahead and just do a little bit of algebra here and then rewrite everything. So I have du divided by 3x squared is equal to dx. Again, the point of U substitution is to rearrange or rewrite your integral in a simpler form so you can use one of the basic antiderivatives. All right, so let's see what we have here. We now have, zoop, okay, we have the integral of 3x squared e to the, okay, u. So I'm going to write e to the x cubed. I'm going to write that as e to the u. And then for dx, I'm going to write that as du divided by 3x squared. So these 3x squareds divide to be 1, and I have the integral of e to the u du, which is great because that equals e to the u plus c. That's just a basic. And then I can rewrite e to the x cubed plus c as my final answer, and then search for it. Now, the thing is that this particular integrand, 3x squared e to the x cubed, if you have done calculus as long as I have, which is longer than every single person here has been alive, maybe even Aaron. I'm going to be 55 this year. I don't know, Aaron, maybe not. But I've been doing calculus since I was, 17 years old. So you can do the math on that. Many people who've been doing calculus a long time can hop from this problem to this answer, and that's okay if you feel confident with it, but it is dangerous on multiple choice because those those options are so similar, and people who write those questions know exactly mistakes that students are going to make. So just verify it maybe by taking the derivative or something. Okay, let's go ahead and take a look at number 3. So on number 3, I have the integral. See, that was the answer. So if you've never worked a circuit before, we should do a little poll, Aaron, and see how many of these folks out here have worked a circuit before.
Yeah,
I have.
why don't you just put in the chat if you, or give a thumbs up or something in the chat, so, or a reaction if you use the circuits.
Yeah. So yeah, if you've ever seen a circuit before, give a thumbs up or something like that. I won't know where to look at that, but Aaron can do the diagnostics and let me know the results. Okay. So this is the integral of x times x squared minus 3 dx, another product. But this one's kind of curious because I know from my algebra days that I can go ahead and distribute here. And so I might do that before I think about going any further. So I'm going to go ahead and distribute. X times x squared is x cubed minus, and then 3x squared dx. Okay, so I have that integral. All of a sudden now, even though it was a product, now I can do kind of a basic anti-differentiation here. This is that reverse power rule. So I'm going to add 1 to my exponent, and then I'm going to divide by my new exponent. So I get 1/4 x to the 4th and minus 3/2 x squared, and then plus c. So that would be my final result there. Those are just little power functions and anti-differentiating. So I'm going to look for number 4. And if you've printed this out for yourself, maybe you're already on number 10. You are fabulous, I must say. Here it is. That was the answer. And so now I've got my next one. This is the integral of x squared minus 3 divided by x dx. Okay, this is a quotient. But when we're anti-differentiating, we don't really want to think about quotient rule necessarily. We want to think about, is this one of our rules? Like, is it log, or is it maybe an inverse trig, or maybe is it a U substitution? Or maybe is it something where I can just divide and rewrite this integrand? By the way, this is what we're going to do. I can divide and rewrite this integrand and then anti-differentiate each little piece. And that's what we're going to do here. So I have this monomial in the denominator. So I'm going to divide. And I get x squared divided by x minus 3 divided by x. So x squared divided by x is just x. Notice how I haven't done any calculus yet. I still have my integral symbol there. And then I'm going to write x dx actually and do something a little different. Minus, now I've got this 3 over x dx. This 3 is just a coefficient. I can slide it out. So it's 3 times the integral of 1 over x dx. Now it's really ready to go. Integral of x dx, gosh, that's actually right here. It's the first thing I wrote down. So that's 1/2 x squared. And then minus the integral of 1 over x dx. Gosh, that's right here. And I wrote that down as well at the beginning. So that's natural log of the absolute value of x. So 3 natural log of the absolute value of x, and then plus c.
So lots of people say they use your circuits, Virge, and
Okay.
some say they even have their students talk to you even though you're not there.
They talk to me. I'm sure they're taking my name in vain.
And then someone made the comment. I don't know if you have any suggestions. They said that they're not able to use your circuits very much because they're hybrid and split. Do you know if your circuits have been adapted to Desmos or any other kind of virtual delivery method?
Well, if they have a secure like Google Classroom or Canvas or something like that, they can post these there, and then the students can just work them on notebook paper. That's what I would suggest. I mean, there's still, good problems. In fact, when I was working these, like I said, I can't remember. I just worked them out like this. Okay. So in terms of adapting them to, what did you say, Desmos or?
Desmos or any other kind of virtual delivery method? I'm not sure what would be.
Yeah, I mean, they could, they could create an activity for their students where they have all of these as like cards on Desmos and then all of the answers, and then they basically do a matching activity. But the purpose of the way I write them anyway is that it's a progression. So it's like a workout. And I coached for many years, and you know, when you plan a practice, you start small, right? And then you kind of, you know, build up, build up, build up. And it's the same thing when if you're going to practice some math, you might not start on the hardest problem, right? You need to kind of build up, and you need to see how things are connected. So anyway, but they can absolutely post these to their Google Classroom as long as it's a secure link that only their students can access, and then ask their students to just work it out on paper, and then maybe even provide the numbers like this, you know, and submit pictures. It's been a challenging year. I'm so sick of all this, all of the, you know, whatever, but I feel hopeful that we're getting back to normal. I've been really lucky in a sense because I've been pretty much face to face, but the problem has been that kids have been quarantined. So, you know, when I think about, oh, well, we did that in Unit 4. Oh, that's when so many kids were quarantined and they were trying to join via Zoom and everything else. It was just hard. Anyway, good. Any other comments or questions?
Nope.
Okay, everyone's done with this one now while Aaron and I were talking, right? No. Okay, x square root of x dx. All right, the integral of x squared of x dx. This is another product, but I'm going to do some algebra to rewrite this so that I can anti-differentiate. So I have the integral of x times x to the 1/2 dx. So I'm really going to add my exponents and get x to the 3/2 dx, or the integral of x to the 3/2 dx. And then add 1 to my exponent, get 5/2. So x to the 5/2, but then multiply by that reciprocal of 2/5. So that's my answer. Yay, if you worked it ahead of us. Okay, here's number 6. And we're not going to work this whole thing necessarily. And by the way, this is towards the end of it. It's got some problems that really need to kind of be worked in reverse unless you're a BC student. So read the directions if you end up doing that. This one right here, the integral of pi 3 squared minus pi x squared squared dx. When students are first doing this in my classroom, they don't have a clue what this is, but I think almost all students right now probably know why a student might need to integrate this, right? Like why would we integrate something weird like that? Somebody put it in the chat. Why would we be integrating this? This is weird. Are you monitoring, Aaron?
Yeah, it's I think people are afraid.
Oh, they're afraid to say?
Volumes.
Yeah, baby. All right. So Melody, are you a student or a teacher? What does Melody say?
She's a teacher.
Yeah. So from the students, you might not have even gotten to volumes yet. So that's, you know, that's usually the last thing that teachers teach. And especially if you're testing towards the end of May, you're probably going to get there pretty soon. But in June, right? But in any case, this is like my outer radius squared minus my inner radius squared. So this comes from volumes. But again, this pi, I'm going to factor it as a GCF and kind of slide it out. And then I've got 9 minus x squared squared is going to be x to the 4th dx. And then it's just a matter of going ahead and anti-differentiating each of these terms. So I end up with pi times 9x and then minus 1/5 x to the 4th. And then you can put your plus c after the parentheses. You got to have those parentheses because of the pi. You can either put it after the parentheses or you can have it in there with the parentheses because it's just a constant. And pi, which is a constant times a constant, is going to be the same either way. Okay. Hey.
So maybe you did that intentionally for when you search for the answer, but is that supposed to be x to the 5th?
Oh yeah. Sorry. I was getting excited about the other thing I saw. Thank you, Aaron. It's a good thing you know a lot about math. Yeah, so that should be x to the 5th. Actually, yeah, let's search for the answer and make sure I have the answer correct. So this would be number 7. So, yeah, so there's number 7 right there. Okay. but I'm going to, in my typical fashion here, I'm going to go ahead and kind of go off-road a little bit, because I noticed this one right away, which is probably where my mind got a little bit distracted. I noticed this one right away, and the integral of tangent x dx. It seems like I should have put it on my list here, right? Like if I go ahead and I do all of my derivative rules on the other side. Which list is this? I have so many lists. Hold on a second. That was the list I made earlier this morning. This is the list I made with everybody today, this just now. If I go ahead and I put the derivative of tangent x on the other side, like if I say y is equal to tangent x dx, what would that answer be? Give me a student. A student needs to give me this one. Derivative of tangent x. It's hard to type it in the chat, but you can just like.
Secant, someone says secant squared x.
Yeah, secant squared x. Good. So yay. So it seems like, and students do this all the time, it seems like going back the other way, you know, it should be like that the integral of tangent x is equal to secant squared x or something like that, but it's not. So let's go ahead and look at the integral of tangent x, and this goes nicely with information about U substitution. Because tangent, we know from previous courses, is the sine of x over the cosine of x. And so I can say to myself, oh, this one, I can't really divide because I'll get back to tangent x, but maybe I could rewrite this using U substitution. I could maybe let u equal, and those of you out there participating are thinking to yourself, well, maybe I'll let u equal the denominator. That happens a lot, especially as we go, you know, into natural logs and stuff like that. And then du dx is equal to the derivative of cosine. And this is why it's so hard. I'm anti-differentiating, and then I'm doing a U substitution, and I got to take the derivative. So you got to keep your, it's very good brain training. You got to keep your head on straight. So now I have to take the derivative of U with respect to X. The notation really helps, and helps talking to yourself as well. This is going to be negative sine of X. So du divided by negative sine of X is equal to dx. This is good because now I'm noticing that I can kind of divide away that sine of x. So I have the integral of sine x divided by u, because I had picked cosine x to be my u, and then times du divided by negative sine x. That divides this negative. I'm going to move outside of the integral symbol because it's like a -1 or a 3 or a pi. So I have the integral of 1 over u du with a negative out front. This is going to equal negative the natural log of u plus c. Ooh, squeezing that in there. So the answer is negative the natural log of absolute value of cosine x plus c. I don't know if I said absolute value back there, but I wrote it. So that would be my answer. And if you want, you could put that on your yellow sheet. You could come over here to the trig and you could say, oh, I better put that down. I'm going to write the integral of tangent x dx is equal to negative the natural log of the absolute value of cosine x plus c. Sorry, I did that so fast. Tell me to slow down if I need to slow down, or tell me to speed up if I need to speed up. I guess, is there anybody saying anything, Aaron?
No, I think we're good. Oh, so a question: why was sine positive earlier and negative now?
Okay. So why was sine positive earlier and negative now? Well, when you're taking the derivative of cosine, you get negative sine. But when you're taking the antiderivative of cosine, you get positive sine. I wonder if this is what they're talking about.
Yep, that got it for him.
Yeah, that's hard. And not only is that hard, but you've got sine and you've got sine. So all the time in class, I'm like, make sure that your sign, S-I-N-E, has a negative sign, S-I-G-N, right? We constantly have to spell that stuff out loud because English is, as hard as math is, I think English is way, way harder. Anyway, let's go ahead and look at just a couple more. Which one did I want to show? Oh, it was over here on the same page, 11. And if you haven't printed this for yourself, you can print it and kind of work it from the beginning. This one, the integral of x divided by x squared plus 1 dx. This one is, I can't, if I had that reverse where the monomial was in the denominator, I could divide, but I can't divide x squared plus 1 into x. If I want to do any sort of division, and I do have some examples of that separate of this circuit, I really need to have the degrees be the same in the numerator and denominator, or have the degree in the numerator be higher. Anyway, so I can't do any sort of division on this one. But I can think about U substitution again. And again, this has come up a lot in our feedback for our lives that we've done. So I think it's not a bad idea to see plenty of U substitution. Let U equal the denominator, x squared plus 1. Then du dx is equal to 2x. And then divide both sides by, well, you're really rewriting it. I don't want to say divide. So I'm going to replace the dx with du divided by 2x, and I'm going to replace the x squared plus 1 with the u. So it's the integral of x over u, and then times du over 2x. So these x's divide to be 1, and then this 2 is really a 1/2, and it can slide all the way out. So I have 1/2 the integral of 1 over u du, which again turns into the natural log of the absolute value of u. So I have 1/2 the natural log of the absolute value of u, and just don't forget to rewrite it with your original x squared plus 1 substituted in for u. The other thing is, when we put these absolute values around the natural log, it's because of the domain of the natural log function. So the domain of the natural log function has to always be x greater than 0, or whatever your independent variable is. So because this expression is always greater than 0, we can just write parentheses there. We don't have to put absolute value. It's not wrong to put absolute value, but you'll see it with parentheses a lot. Okay. There's so many good ones here, but I do want to do just one last one and then switch to something else. And that is, I think it's on the front page, and something that came up in our teacher community this morning, which is why I want to talk about it. This is the integral from 0 to 3 of the square root of 9 minus x squared dx. And for the teachers who are on this call, if you're not on our Facebook group, it's really robust. Aaron's on there, people asking so many good questions, and no shame in asking questions. Teachers are the masters of asking questions. We ask questions constantly. And anyway, this came up, like, how are you supposed to do this? Because you can't do a U substitution. You can't do any sort of algebraic simplification. And there's some more very advanced techniques you can use, but they're not part of our curriculum. What are students supposed to do in this case? Well, students are supposed to recognize that x squared plus y squared equals 9 is the equation of a circle. And if you solve it for y, you get plus or minus the square root of 9 minus x squared, which means that this integrand is actually the top half of a circle from -3 to 3, centered at the origin, because that's what x squared plus y squared equals 9 is. So geometrically, we never want to forget about our geometric ways of figuring out these definite integrals. And this happens to be a definite integral, which is why we can use some geometry here. So this is going to be a quarter of the circle pi r squared, where the radius is equal to 9. So a quarter of that. So 9 pi over 4 would be the answer there. And there's several definite integrals to do as you work through some of the other practice that is available here. But I think what I'd like to do is, if there's any questions here, let's pause for a moment and see if we have any questions before we switch to our Desmos activity. And I am going to give, after our Desmos activity, 4 more examples of some advanced techniques written in very fancy form on the back of an envelope. But if there's anything, please put it in the chat. I'd be happy to answer anything before we go to our Desmos activity.
And I think for everyone watching, I think it's important, and I don't think you would disagree, Virge, that you it's not like you teach calculus all day, like all day every day during your actual teaching career, and your students are not like all making 5s like every single day.
No.
I
Yeah,
think
you want to know the spreadsheet of our mock exam? Okay, here's the frequency table of our mock exam. Okay, this was a score. This was the frequency. Ready? 3 1s, 9 2s, 3 3s. That's a 4. 3 4s, and 3 5s. I think, at least at my school, there's no sort of gate for taking AP Calculus, except you have to have taken like the pre-calculus or whatever, but you don't have to have made an A in it. I'm begging kids to take AP Calculus most of the time. I just know that it's, even if they're making in this 2 range, they're going to be much better off in college, having struggled and gotten that before they got there. Go to Ole Miss or, University of Kentucky. I live where Ole Miss is. I mean, you're going to sit in a calculus class with 100, 150 other students. It's nice to have that background and know something anyway, right? And I teach regular Algebra 1 students that are 10th graders, and I teach 8th grade Algebra 1 students that are going to be, AP students one day. So yes, I have and I'm the department chair too. So we always, in our school, we try and teach 2 preps hopefully each, and then we also try and teach some of the accelerated or advanced kids, and then some of the other kids. Like, that's how we've tried to stratify our department for equity. All the students are like, snore right now, this is so boring for them. But I think for the students to know, like, I only have like 23 or 22 AP Calculus students. And this is how they do. It's actually, these guys will hopefully, a lot of them hop into the 3 category. I think it was a wake up call for them. But my scores pretty much look like that. It's like a stats
I think
class.
it's really, really important. And I don't think a lot of times students and teachers probably think that, oh, well, you're just an everyday, like just I guess for lack of a better word, average, typical teacher in terms of what you teach and your student performance. So yeah.
Here's the thing. Every student knows like nothing at the beginning of the year, right? Like, in terms of like the calculus. So like, you're starting always at ground zero, and that's and also these students are very involved. I have 2 tennis players that just won states. They're going to be then, and they've missed class a lot lately, and they're missing class next week to compete at the state level for the individual competition. I have other students who work 30 to 40 hours a week. Like, I have all different kinds of students, so they're taking other AP classes that got commitments all over the place, so they've got to spread their time out, and that's the reality of life, right?
Yeah.
So I know there's a lot of students on the call who got up early on a Saturday morning. Good for you. And just trying to get a little last minute practice in. So
All right, during our stall, we had 2 questions.
okay.
First one, for the problem integral of x cosine x, is it permissible to use integration by parts, or is there another method that has to be used?
Oh, so this one right here, this is actually, you can see I didn't even get that far when I was working it. If you read the directions, it says the last 4 problems are challenge problems and may involve geometry, integration by parts, and or partial fractions. These are BC techniques and or calculus 2 techniques when you get to college. So the only way to work this is integration by parts that I know of. However, once you're that far in the circuit, you only have like 4 answer choices left. Differentiate all of them and see what you can match up to complete the circuit. That's what would be my advice to an AB student or an AB teacher. But the AB teachers probably remember how to do by parts, so they can do it. Also, if there's time at the end of their course after the exam, a lot of AB teachers like to teach integration by parts to their students, or partial fractions, just to give them some more tips and tricks before they get into college calculus.
And then the other question is it okay to teach half-angle trig functions and double-angle trig functions?
You mean in terms of anti-differentiating? I mean, yes. It's not going to show up that much on the AB exam. So if you're crunched for time, I wouldn't worry about going over it. But BC folks definitely will need to do some of those, I think.
Okay.
especially the half angle ones.
Yeah. And those were all.
Okay, thank you. Okay, so we're going to try this. Also, I'm not that experienced, I guess I should say, at doing this teaching in this way. I think you guys should be able to see the Desmos screen now.
Yep.
Okay, and let me make sure, hold on a second. Let me make sure, okay, we've got it anonymized. Anonymized, is that a thing?
Yeah.
Okay, we've got it anonymized, but so okay, yeah, we've got, no, what we're going to do is I'm not going to anonymize it. Actually, I'm not going to anonymize it. So what I want you to do is put your name in, but if you're embarrassed, put your name like something that only you would know, like maybe put your dog's name or something like that, but make sure it's G-rated or Aaron's going to kick you out. But so I'm going to not anonymize it. Okay, so this IMO TEP or whatever is if I'm going to do this. So see, it's Brett. I mean, it's okay. We're all friends here, so it doesn't really matter. But if you feel nervous about getting called out on something.
And the link
All
is
right.
in the chat now as well. So
yeah, so the link is in the chat, or I'm going to leave this up for a little bit as people get in. So as go ahead and start working on it. As you start working on it, what this is if you watched any of the AP Daily videos when I was doing, I believe it was in Unit 2, some of the derivative rules, I made up a little card matching thing, something that I might do in my own classroom, and then I transferred it to Desmos, and I kind of leveled it up a little bit too. And so the teacher who was asking about the circuits, you know, I've learned a lot about how to make all of my matching activities and stuff on Desmos, and matching activities are really good for that, actually. Circuits, you know, if it's kind of a review circuit, it doesn't really matter. But if it's a progressive circuit where you're really trying to start small and kind of go big, it's harder to do on Desmos, I think, as a matching activity. Anyway, okay, so this link is in the chat. Okay, so the objective here, Brian Fisher, that's my husband. I had said, so this first person who has it wrong, that my husband is always so helpful. I send him stuff to print at home, and he thought I was supposed to print this, but it was really, I just had forwarded the email that I had sent to you, Aaron. So right here, if I go to here, we can see how people are doing. And looks like some people have some wrong matches, and that's okay. And then if I go here, I have to remember how I do these things. Maybe I should go directly to my husband's set of cards. Yeah. All right. So can everybody still see this, Aaron?
yes.
Okay. So this is exactly what we've just been working on. It looks a little different though, because there's no integral symbols, but you know, the derivative and the integral are part of the same, two sides of the same coin. So if we want to know, for example, the derivative of the inverse tangent of x, this one that I'm moving around right now, we would go ahead and search for it. And it's on our yellow sheet. So I'm not going to say what it is. You can look at your yellow sheet yourself. Yeah. And this, you can write Desmos activities that are self-checking. We're going to do one next that is self-checking, but I've got these cards up here so that you can see for yourself that you've made some wrong matches. Ooh, my gosh, this is impressive. You guys need to all buy yourself a treat after this session. Okay. So again, I'm going to go into my husband's stack that he hasn't matched yet. Somebody tell me who feels pretty confident that which one the inverse tangent of x should go with. Derivative of the inverse tangent of x. That means the integral of what would equal the inverse tangent of x? Or sorry.
Well, someone is joining. Someone
Sorry.
is joining the meeting that may be able
Oh
to answer that
my
question.
God, this is so exciting. Can you unmute him, or does he have to stay muted?
We'll give him co-host privileges here.
Hi, Mark.
Hey, I have the ability to unmute myself. All right. I tried it first. It was like, you don't have the ability to unmute me.
So Mark, look, I'm in my husband's office because I was having the same connection issues.
Oh,
And
no.
I think it's because of, I think honestly, like our little router thing or Wi-Fi thing or whatever you want to call it, like got honestly moved like an inch. So when we're working together later this afternoon down, because we were kind of blipping in and out yesterday, weren't we, last night when we were working? So we need to see if I can fix my internet. Okay, problems. We got problems. All right, but my question was, and maybe somebody put it in the chat, if I'm trying to match this derivative of inverse tangent of x, what would it go with? And then maybe Aaron can tell us.
Of course, my wife called right as I jumped in.
So Mark's wife is a referee for big track meets, like college level even, right, Mark?
Mhm.
Yeah. So he's all by
Honestly,
himself.
this is either a high school regional or a track meet or a
Yeah,
college
so he's
meet.
all by himself with the kids this weekend. All right. So did anyone put in the chat
maybe they're so hard working at matching them that they are not able to put it into the chat right now.
Yeah, that could be. Let me check their
Oh,
progress.
there's an answer.
There's an answer.
Yep, there is.
And it looks like a very strong one.
Okay. So this one right here, we would want to pair the derivative of inverse tangent with 1 over 1 plus x squared. Yep. All right. And I think with a lot of these Desmos activities, my advice would be to just, match the stuff that you know first and then see if you can, hunt around and do the rest.
I sort them a lot too.
Before you even start, you mean?
Yeah,
That's a good point.
I actually put in a suggestion to Desmos that they have automatic sorts when we open these, so everyone starts with the same hand. And I got an email back saying that's a really good idea. And
we'll see if it happens.
That's where we're at right now.
Well, you mean sorting like all the d,
right? Like all the dx, all the derivatives together,
and the teacher could turn that option on, maybe.
Yeah, so you could have a preset sort so that it's not just the.
So it looks like this, maybe.
Right. So if you're doing a race or something, everyone's starting at the same bar.
Yeah. All right. Okay. Ooh.
Can you share your screen where it shows how the students are doing?
Yeah, am I doing that right now?
I think so.
Yeah. So one thing my students do is they figure out, well, I'm not, you guys aren't anonymized, so it doesn't matter. But so like you can like move a card. You can
anonymize them up in the corner if you wanted to.
I did, but I told them kind of while you were coming in, that I said, well, it doesn't, this way they can kind of see how they're doing, and it's okay. They're up early on a Saturday morning. It's
exactly,
they're just trying to learn something extra. So yeah, so like if you go ahead and like this one right here, for example, this is on Jaden. I am totally not calling you out, Jaden. I just happen to click on you. This is a really good match because the derivative of inverse sine is 1 over the square root of 1 minus x squared. So these two like kind of go together. They really do. But the problem is that you would have had to have used chain rule here on the derivative of inverse sine of x squared. So it would end up being 1 over the square root of 1 minus x squared, and then times the derivative of x squared, which is 2x. So these two like kind of go together. They're kind of in the same family. So right idea, but you gotta search for one that's positive first of all, and then don't forget about chain rule in here is another thing. Okay, let's see if I can click on somebody else. Boots. I had a dog named Boots. I told them to maybe put their dog or cat's name if they didn't want to put their own name. Let me see if I can find the one set of cards that you have not matched correctly. You have a lot of good matches. It's this one right here. So this one right here, the derivative with respect to x of the square root of x squared plus 1 is going to be 1 over 2 square root of x squared plus 1 and then times 2x. So the 2's do cancel, but this x ends up in the numerator. So I think this one needs to match with this one up here if Boots is still with us. Oh my goodness, Hannah. She's getting organized. I can see it.
That's the sorting mode. Yeah.
Yeah, exactly. This is good. Okay. So somebody should put in the chat, like I've kind of given a couple of tips here, but somebody should put in the chat if they're curious about anything, because we're going to kind of move on from this and do a couple of other techniques. Actually, we'll probably take a quick, what do you think, Aaron? Take a quick break?
Sure, yeah.
Yeah. So we're going to take, what did you say, Aaron? Like a 5 or 7 minute break or something like that? Yeah.
That will work, yes.
Okay. So 5 or 7 minute break. And I'm going to leave this kind of displayed. But go run and go to the bathroom or go get a soft drink or something like that. I got my water right here.
So right around, yep, almost right about 10 after, that'll be 8 minutes, I guess, but that'll give you time to continue working on the sorts. If you have any questions, go ahead and put those in the chat and we'll get those when we come back.
Yep. Mark, what's your background?
That is Euless Hall, which is the home of the Honors College at Michigan State.
Mm.
And the turret right behind is actually the spiral staircase between the 2 floors.
Mm-hmm.
It was originally either botany or entomology. It was either insects or just general botany building. It was part of it. Amazingly, it was an ag building, right?
Was it looking like a silo or something like that? The
Well,
turret?
no, because Michigan State was the first agricultural college.
Okay, so I don't know if you heard this story on NPR yesterday, but we heard it. So there were seeds that were planted by a Michigan State scientist
it's
like 100 years ago.
Beals, because we have 3 botanical gardens, and my favorite one's named after Dr. Beals. Yeah, he started the experiment 141 years ago. And they've actually expanded out. It was supposed to be every 10 years. And now the latest batch of seeds, it's been 21. I think they're going to wait another 21 for the next batch. But yeah, he buried a bunch of seeds in sterile dirt in bottles in the ground, and they're digging them up and they replant them and see if they're viable. And so far they haven't. And last time there were only 2 species still viable, but 2 species grew last time they did it.
Yeah, it's incredible.
But it's so cool that when you start talking about the scientific method and having a legacy, and you start an experiment during this, during or right after the Civil War.
Yeah,
it's still going. That's just.
It's something for these students to think about if they're still on with us, like, what's your legacy, And if you think about Hamilton, he knew that he wanted to have a legacy when he was the age of a student. Back when he was 15, 16 years old, he knew he wanted a legacy. I think a lot of people think about their legacy like right before they're dying. But yeah, it's just an incredible legacy. And these kind of students who are with us on a Saturday morning are the kind of students who are thinking about their legacy. Like, what are they going to contribute? How are they going to help the world? How are they going to change things? And those are such important questions.
He knew he was starting an experiment that was going to outlive him, obviously.
Yeah.
But he didn't realize that it was going to get extended. It was going to be such a successful experiment that it was going to be modified and extended.
Very true. Very true.
His predictions were that he knew they would last. He didn't realize that they were going to last as long as they have.
Right. But I think teaching is such a great way to, extend your own personal lifetime, because of course, if you teach kids who become teachers like you and I both have, it's kind of like generational,
about
right?
Coaching trees, right?
Yep. Oh, definitely.
So you have a teacher tree.
I think when you're a young teacher, you don't think about that stuff. You're just trying to keep your head above water. But then when you're an older teacher, you think, oh my gosh, I need to get some transplants for me, like I need to figure out who in this classroom can take over. not literally into my classroom, but figuratively, who's teaching the next generation, you know? And so you start really looking for those kids, and some of the kids on this call might be that person. So are there any questions coming into the chat? Doesn't look like it. Okay, we're still on break. So again, this is one of the ones that does not have, you know, check your answer at the end. But the one we're going to do after, well, the one that we're going to do in a little bit does have a check your answer at the end. And it's one that Mark wrote. And I actually got it right this morning when I did it. First time I got it right. First time I got it right after doing it. When did you write it? Like, well, you wrote it with cards, but you put it to Desmos.
I wrote it with cards 2 years ago, and then I digitized it last summer.
Right. And so I actually worked it for the first time, probably like in January, because I knew I was going to be teaching slope fields and differential equations in February. And I was like, oh gosh, I kept getting them wrong. It's so easy to pick the wrong thing. Anyway, this morning I felt pretty good when I did it. I was like, yay, I got them all right.
It's a good feeling when they're right. Like, it's that same feeling you get when you finish a circuit.
Yeah, definitely. And I think that kind of practice is, you know, even like with fitness these days, like people have to wear their Fitbit or whatever to monitor their steps, because it is a good feeling when you hit that goal. So same idea. Did Aaron actually leave, or did he just close out his screen?
He muted himself. He may have, I don't know how
he said 10. Oh, he's back. Oh, he went and got more coffee. Hi, Aaron.
Hi. Yeah,
that's fine.
All right. So I know I'm leaving stuff undone, but there's still plenty of time for the AP before the AP exam, and you can always email me or get with your teacher. And I'm going to leave this activity open for like 2 weeks, so you can share it with your teacher and that kind of thing. So in any case, it looks like lots of people have made some good progress on it. So anyway, I'm going to switch back, and you might want your notebook paper for these last couple of problems before we go into another Desmos activity. And these were ones that I just was thinking about this morning to wrap up techniques of integration. And these honestly don't come up that much the way the basics and the U substitution would, but they do.
Quick Desmos question, Virge.
Yeah, sure.
So is there a way for the students to find out if they've done it correctly or matched them correctly?
Besides looking at my screen just then?
Yeah. Like
okay,
if they
hold
choose
on a
to do it
second.
later.
They can have a self-check on it. I don't know if that one did.
That one doesn't have a self-check on it, so they can email me. I'd be happy to look at it for them.
Okay.
Yeah.
The one she's about to show, or are you going to skip it, or are you going to show it?
No, I'm going to show. You mean
the one she's about to show has a self-check on it.
Yeah. But the one we were just doing, I was kind of sharing, I'll go back to it. The one we were just doing, I was sharing the screen. So if you remember what you put as your name, you could check right now to see if you're right. Okay. Like Nick is right, Sigrid is right, Dream is right, Vicky is right, Barb is right, you know, Tate, Boots, Charlie, Ellie, you know, but Ryan, so this Jaden's really close. Okay. Anyway, so email me and I'll leave this is open for like 2 weeks. So email me and I'll be happy to tell you if you're right, or I can even send you information in the chat. Like here's Reagan. I'm sorry if I'm not pronouncing your name right, but Reagan's got stuff organized. There should be just 2 cards per stack. That's why it kind of looked weird, but she's probably got them organized, or he's probably got them organized a certain way. This one's not right. So I can chat and I can say the derivative of inverse cosine has a square root in the denominator. I've got probably all of my pictures. Can you guys see that? Square root. Okay. And then, yes, I'd be happy to chat with any students as they're working on this. Okay.
Right,
but my email was at the beginning, and Aaron will show my email at the end as well. And maybe even you have it on your own stuff. Okay. All right. So just to talk about a few other ones, and especially because they recently came back onto the AP exam, algebraic techniques, such as if you had an integral like this, the integral of 2x plus 1 divided by x squared plus 1 dx. If you try to do a U substitution on that, it's not going to work because the derivative of x squared plus 1 is just 2x, and you have this extra plus 1 lingering up there. It could be a plus 10 or whatever. This one, it's so simple, but it's hard. This one, you would just go ahead and split up the numerator. Okay, so you would just go ahead and rewrite this. This is nothing fancy, but using a little bit of algebra 2, rewriting the numerator or rewriting the fraction as 2x over x squared plus 1 plus 1 over x squared plus 1. You would need a U substitution on this part and an inverse. This would be inverse tangent on that part. Another one that we just saw one like this in our AP live on whatever day that was. What's that, Thursday? We just saw one like this on Thursday. So if you haven't yet watched those AP lives, you know, you can binge watch them this weekend or whenever makes sense for you. But this is a situation also of it looks like a U substitution, but there's no way that I'm going to be able to cancel anything out when I do that because I don't have anything in the numerator. But this is when I would rewrite the 26 as a 25 plus 1. So it would look like this. And then I have dx. So this right here can be factored as 1 over x plus 5 times x plus 5 or x plus 5 squared dx. And then this is of the form where it's going to become an inverse tangent when I anti-differentiate. Another one that we didn't see just now, but that happens, integral of x squared minus 1 over x squared plus 1 dx. This one, I would factor in the numerator and then divide so that you're really just anti-differentiating x minus 1 dx. And then finally, if you had something like this, the integral of x squared plus 1 all divided by x plus 1, actually, well, it doesn't really matter. I had it as x minus 1 on my... Again, I'm not finishing these off. I'm just saying kind of what the techniques are. This one is really one where you have to do some division, long division, but it's like short long division. You take x plus 1 and you try dividing it into x squared minus 1. X divides into x squared x times. So I get x plus 1 times x, which is x squared plus x. And then I subtract. Anyway, I'm not sure actually that this one will work out. I kind of changed it from earlier today. But in any case, there are times where you have to do long division. So if you want to see a better example of that, email me and I'll dig one up. I just kind of came up with those because I thought there weren't as many of these kind of examples on that mixed circuit that I gave you guys. So I wanted to just, you know, prime your brain to think about some of these singleton cases. Okay, so we're going to go transition into this like slope fields part of the time and the differential equations part of the time. This particular activity that we're going to do on Desmos is I'm going to talk through a lot of it first with you. Let's see if I can share my screen and get you started on it. So it's this one right here. And Aaron can probably put it in the chat.
It's going there now.
Okay. Sorry, I just did that and I didn't mean to. And
there
this is kind of like the other one. It's just one page. And like Mark said, this is the one that he wrote. It's like everything comes at you all at once and it's kind of disorganized. So you might on your own personal screen kind of sort everything out. Instead of a one-to-one match like the last activity, there's actually 3. So there's going to be a slope field and it's going to match with a differential equation and it's going to match with a verbal description. So I'm going to go ahead and that's all there is. There's that and then there's the check yourself. And I'm going to unanonymize this. Is that a thing? Yeah. Kind of a mess. This is why Mark said, and so we've written a lot of these for, especially for Algebra 1. And we've actually kind of broken them into a couple of separate
I actually
matches.
put that in the chat a little bit ago for one of the teachers who mentioned they tried to use it on their phone.
Oh yeah, no, not on the phone. Yeah, that's a good point.
If I made a smaller version of this one, because I've done that with a bunch.
To where they can do them on their phone.
More or less, yeah. It's still tough, but even on a like a 13-inch laptop, it gets crowded. One thing that does help if you are having issues and you're on a computer, like even with Virge right here. I don't know the Mac shortcut, but if you're on a Windows machine and you hit Control- to shrink your browser, it shrinks the size of all the cards a little.
So it's easier to see more stuff.
Yeah, and if you click on a card, the card blows up. It zooms in.
Yeah. So if you click on that one.
Yeah. So you
oh, that's interesting. Look at what I do. Oh, there it goes. It took a little minute for it to
you can shrink them so they're a little smaller, and then use this to zoom in on each one individually as you move around.
Mm-hmm.
Yeah, here's a smaller screen polar card match. Oh, that's a polar one. Never mind.
So here's my advice on this one, and this is just like by doing it wrong so many times. My instinct was to go to the differential equation, since that's like the calculus part, right? And then from there try and match graphs to it. Instead, I went to the verbal descriptions first this morning, and I read them and I said, let me see if I can find a slope field that matches that verbal description. So for example, this one, right? Can people see my screen if I'm doing this?
Yeah.
Okay. So this one right here, it says horizontal slopes along y equals -4 and y equals 4. Okay, so horizontal slopes, that has to be like going straight across along y equals -4 and y equals 4. And then dy dx is greater than 0, so the slope is positive for y is greater than 4. And for y is less than -4, and the slope is negative, dy dx is less than 0 for in between -4 and 4. So we want to find horizontal slopes along y equals 4 and y equals -4. So that looks like it would match with this one. Oh my, I can't even believe it, but it's right here. I've got these horizontal slopes at y equals 4.
See, this is the one that made me send that email to them, because it would be so nice if this opened up.
Mm-hmm.
And all the slope fields were grouped together, and all the verbals and all, because they quit pulling the equations out of the verbals is sometimes hard for the eyes.
Mm-hmm. Yeah, so that one definitely went together. And then if I pick another one that's kind of like it, horizontal slopes along the x-axis. No, that's not that similar. Which is the one I'm looking for?
Right?
This one.
Yep.
Horizontal slopes along x equals -4, x equals 0, and x equals 4. So I'm looking for the slopes to be horizontal, but at vertical places. X equals -4 is a vertical line, x equals 0 is a vertical line, and x equals 4 is a vertical line. Okay, so let's see what I can find.
Colder.
Oh, I see it. There it is. It's right here, right? Isn't this it? Okay. So there it is. And those two go together. Okay. And then now I've got those two matched. Now, if I think about, for example, this dy dx right here, remember dy dx is the slope. And so this dy dx equals y squared minus 16. This is telling us that the slope is equal to y squared minus 16. That means that dy dx is 0 when y squared minus 16 is 0, which means that dy dx is equal to 0 when y is equal to plus or minus 4. So I'm wondering if this can match with either of the ones I already have collapsed. Don't you think? It should match with that one? Yes?
That's an excellent choice.
Okay. This is how I did it this morning, which took me like 4 times to get it right. Like I was like in this crazy manic trying to do it like this because I knew I wanted to do it with my students the next day. This is how teachers usually are. They're trying to manically do it like this. And because I finally did it many times ineffectively, I guess you could say. Now I can do it right. All right. When you go to this part next, it'll tell you how many you have correct. I don't know if it will.
No, it
Oh,
doesn't. This one, it just tells you if they're right or not.
Yeah.
So you might still have to reach out to Virge for how many or something.
Right. And so this one just tells you how many, just tells you if you're all the way right or not right.
If it's all the way right, it'll say you're correct.
Yeah. Okay. So let's see how anybody else is doing so far. No judgment, no judgment. Ooh, see?
And I like how you can see the people that are kind of using your strategy because you can see the pairs, that third slot waiting.
And, okay, now here comes some true confessions here.
I guarantee Hannah's organizing.
Yeah, Hannah was organizing last time too. So look at Lucy with a three-way. Very good. So one of my students, this took my students like more than a class period to finish with a partner. And we only have regular class periods. We're not on block or anything like that, but it took them a long time. And so they came back to me later in the day, like, when they had some free time or whatever. And one of my students said, I'm just going to start this all over again. And she like did match all the verbal descriptions first. And wow, it was much, much better when she did that.
Funny. And it's when I do these in mine, and I do some other card matches, I never recommend a method because while that works for us, some people are just gonna be able to do the others first. And
me neither, but I did it so wrong so many times. I figured I'd say how
it
worked for me. Yeah. So anyway, now let's talk about this little guy over here. Okay. Let's talk about dy dx is equal to negative xy. And I want to talk about dy dx is equal to negative xy because we already thought about this one on that area problem that I did earlier when we did the integral from 0 to 3 of the square root of 9 minus y squared. So if you're going, great guns, matching all this stuff, fabulous. But if you're kind of like, okay, maybe I need to match another one correctly, and let me listen to what she's saying here. I'm going to go ahead and kind of talk about this one because this particular one comes up all the time in calculus. And I'm actually this activity is still going, but I'm going to unshare my screen and go back to my overhead. So I'm talking about this differential equation here, dy dx is equal to negative xy. Remember when I did that area problem, the integral from 0 to 3 of the square root of 9 minus y squared dy, I think it was. Or maybe it was dx. It might have been dx. I guess it was dx. And I said that this was the top half of a circle, and then we found that area. Okay. If you think back to what I wrote down x squared plus y squared is equal to 9, and I algebraically solved for y. But we many times take the derivative of this implicitly. And we take the derivative sometimes with respect to x, sometimes with respect to t, depending on what we need. So I'm going to take the derivative of this with respect to x. So I'm going to get 2x plus 2y dy dx is equal to 0. If I subtract 2x from both sides and divide both sides by 2y, then I actually get negative x over y. I get negative 2x over 2y, which simplifies to negative x over y. So when I see dy dx equals negative x over y, I think to myself, when I look at that slope field, I should see concentric circles because the slope field is like the skeleton of the original function.
Can I step in a little bit there?
You can, but
please see concentric semicircles.
Okay, yeah, exactly right.
It's very important that you can't.
The solutions. That's right. The solutions would be either the top semicircle or the bottom semicircle. But it will look like a bullseye. You know what I mean? Like the actual slope field itself, I guess, is what I was trying to say there.
That's a real common misconception that teachers, it's more a teacher thing than a student thing because they're so familiar with it.
Yeah.
If they see that and they think it's like, no, solutions are functions. In the bottom half, you get the same derivative. And the bottom half and top half might not match. You might have a situation like this, and the derivative is still negative x over y at every single point. And
correct.
I just want to throw that out there.
So the solution to a differential equation has to be a function, definitely. And we'll know, what the solution is based on that initial condition and being able to solve for that.
How about its friend negative y over x?
Well, right. So that's right. And the way that Mark wrote this, I think, is really lovely for, noticing these patterns. So there's what looks like a bullseye. And I'm so glad that Mark's here because he reminds me that, the solution is never going to be a circle. Can you guys see that when I'm doing that with the cursor?
Yeah.
Okay. All right. The solution is never going to be a circle. It's going to be a semicircle, either the top half or the bottom half. Okay. But this one seems awfully familiar. So what happens? How did that come about? Well, algebraically, you might have had something like x squared minus y squared is equal to 9, right? And then when you differentiate that, this might be the result. I don't know. I got to think about it a little bit. Would that be right, Mark?
Nope.
Nope. I was going to say, I'm doing the derivative in my head and I'm like, no, that's not right.
No, now if you have my hard copy, that's like 12 sets that just there's no way to fit that on screen. I've got the hyperbola, but this one is not the hyperbola.
Not the hyperbola. Yeah, because the hyperbola would just be positive.
Right. So it has all the same signs as the circle. That's one of the things. So in the first quadrant, they're still all negative. But the relationship's the inverse relationship. So your x-axis, when x is 0, right, they don't exist. And when y is 0, you get 0. So the x-axis is now horizontal and the y-axis is where it's undefined. And so if you expand the circle one again, so you'll notice in the circle is I move away from the origin, they get steeper, right?
The slopes get steeper,
I go to the right, they get steeper. As I go up, they get shallower because as I go up, y is getting greater, so the denominator is getting bigger, right? And so I get shallower slopes. This one's going to do the opposite. As I go up, they're going to get steeper, and as I go right, they're going to get shallower. But the signs will be the same, and there you go.
This one, right? Maybe.
So that's a lot of times you can look at that one, especially with those fraction ones. As x gets larger, these are going to get smaller. As y gets larger, they get bigger. And of course, always looking for those horizontals and undefined locations.
Yes, that's a good way to do these as well. Like
in signs too, right? Like first quadrant, y and x are both positive, but has a negative in front of it. So first quadrant, they're all going to be downhill slopes.
Yep. Or like this kind of a thing here, dy dx is equal to x squared minus xy. This one, where is this going to equal 0? Well, set x squared minus xy equal to 0, factor out the x, and you're going to get x equals 0, and then x minus y equals 0. So this is going to equal 0, where you have on the y-axis, x equals 0, the slopes will be 0, and then also along the line y equals x.
Yes.
So,
and Mark Howell has a wonderful activity on that designing slope fields with those features.
Yeah. Okay. All right, let's see how folks are doing. Just out of curiosity. Looking good. This is hard, and we're not going to spend 2 hours on it, but some of you guys are going to spend 2 hours on it because you're that good. And please email me, and I will help you.
We got a couple people finished.
Yeah.
There were some check marks in that other screen.
Yeah, we have a few things in the chat. What do we have? Oh, just Aaron to everybody. Okay. All right. We only have another half hour, and I'm not going to keep you all day, although Mark and I can do calculus all day.
I'm actually going to jump off.
Okay.
I'll go say hi to Brian, and then my 5-year-old just came through and requested some stuff. So
got to help the 5-year-old. Okay. So the last thing we're going to do today is kind of go a little bit more in depth with differential equations. And so this particular activity is is one of the things that Aaron shared with you. And it's also a very long activity. We are not going to obviously do the whole thing. It takes my students usually like 2 class periods to do it. But I gave you guys not the student version, but the teacher version. So my very aggressive students can be checking themselves and stuff like that, because I do have all the answers. I put that in there as well. Okay, but this is about differential equations, and it's got 2 focuses. One focus is to look at some differential equations. And of course, I wrote down, where did it go? I wrote down a differential equation right here. dy dx is equal to negative xy. This is called the differential equation because it's got the differentials, you know, in the equation. When you see a differential equation, it's important to notice that you're looking at a differential equation. You're looking at a formula that is the slope, okay? And sometimes when you're looking at a differential equation, you see both of the variables, like you see both the x and the y. Sometimes when you're looking at a differential equation, you see only the x. And sometimes when you're looking at a differential equation, you see only the y. That was true on that activity that we were just doing on Desmos. And I think if you can take a minute and assess what it is you're looking at, then you're going to have good success with differential equations. And so what I mean by that is sometimes you see dy dx is equal to x squared plus x plus 7. In this case, I see only the independent variable showing. And of course, we could see dy dt is equal to t squared plus t plus 7. If you see dy dx is equal to negative 0.05 times y minus 70, then I see only the y showing, which is what we say is the dependent variable. So this is the independent variable, the dependent variable. It's really different if only the dependent variable is showing, especially when you try to solve this differential equation and you have to separate. This one, to solve this differential equation, is really straightforward. And then finally, like that example with the circle, dy dx is equal to negative x over y. This is a situation where both the independent variable and the dependent variable are showing. So in terms of solving this differential equation, again, kind of like this one, there is definitely some algebra and rewriting to do in that case. Okay, so the first thing that students do on this activity is they sort all of the cards, and there's 12 of them, into either independent only, dependent only, or both independent and dependent. And then once they've sorted all the cards and they've checked the results, then they work on each individual problem. So I'm going to move all this along. We're only going to look at a few of these examples and kind of talk about the sorting of them, and then also actually working a few of them. Okay, so here's example A. So let's classify this. It says the velocity of a particle traveling along the x-axis is given by dx dt is equal to negative 2t plus 3 for t is greater than or equal to 0. If the particle begins at x equals negative 5 when t is equal to 0, what is the particle's position when t is equal to 2? So here, as I'm looking at this differential equation, my independent variable is t, and all I see for variables on the other side is t. So this would be independent only. I only am seeing the independent variable. This differential equation is defined exclusively by the independent variable. Let's look at this one, the card B. And it says the particular solution y equals h of x to the differential equation dx is equal to negative h plus 7 to the 3rd power, which passes through the point negative 3/2 negative 6, has the form h of x equals negative 7 plus 2x plus c, all raised to the negative 1/2. Find the value of c. Okay. Here's my differential equation. There's a lot of stuff going on here, but here's my differential equation. There's another equation here, but this one's the differential equation because I see these differentials. My independent variable is x. My dependent variable is h. This equation is all in the form, all in terms of the dependent variable h. So this is dependent only. Let's look at this one. It is a truth universally acknowledged that acceleration is a derivative of velocity. In other words, a is equal to v prime. A particle's acceleration is given by the differential equation v prime is equal to t squared v. Determine the velocity of the particle when t is equal to 3, given that when t is equal to 0, v is equal to e squared. Now, this is the differential equation right here, but we don't see the differentials explicitly. And for the most part on the AP exam, the differentials are written out for you, dy, dx, dx, dt, dh, dt, whatever. But sometimes when you're verifying, particularly on the multiple choice, you'll see like a y prime and a y double prime and things like that. And those are showing us that you've got the first and second derivative. Well, what is v prime? V prime is the same as dv dt, and that's t squared v. So we've got both variables showing, both the t and the v, both the independent and the dependent variable showing here. I rewrote v prime as dv dt. Okay, I've got one for you to do. There's actually 12 altogether. You can do them all, but this one says, and I hope I folded it okay. Yeah, I think we can see it all. This one says, fold this back down again. Let y equal f of x be the particular solution. Let y equal f of x be the particular solution to the differential equation y prime equals 2 square root of 3y minus 1 with initial condition f of 0 is equal to 37/3. Find the particular solution y equals f of x and then evaluate f of 1. So do we think this is independent only in the differential equation? Do we think this is dependent only? Or do we think this is both independent and dependent? You can put it in the chat. So I think I saw one in the chat. We need a few more votes.
So someone says dependent only.
Mm-hmm. Yep. 2 people say dependent. Oh, we got a whole bunch of
Okay.
people. Oh my goodness.
There we
Okay, yay. Everybody's so good. Okay, so I have that little sticky wicket right here about this y prime again. So dy dx really is equal to 2 square root of 3 minus 1. And so what I'm seeing here is that y, the dependent variable, is the only thing that's showing in the differential equation, which means our strategy for solving is going to become a little bit different. Okay, so what do we do with differential equations? Well, of course, we can generate slope fields like we saw, and we can do lots of other things too, like solve them. A lot of times is what we need to do. But I want to show you this example here, and we're going to actually work this one, and we're going to work several, as many as we have time for. I've got 4 planned. We'll see if we can get to all of them. And this is I. No? Yeah, this is I right here. So we're going to actually work this one. All right, on I, it says, write the equation of the tangent line to y equals w of t at t equals 0, given that w of 0 is equal to -7, and dw dt is equal to 2t w plus w. Then use the tangent line to approximate w of 1. So I see my differential equation right there. I notice that w and t, my dependent variable and my independent variable, are both playing a role in the differential equation. But I'm not being asked to sketch a slope field, or I'm not being asked to solve this differential equation or find the particular solution. What am I being asked to do? I'm being asked to write the equation of the tangent line. What do I need for a tangent line? I need two ingredients for a tangent line. I need the point and I need the slope. Did they give me either of them? They gave me the what? Are people in the chat?
Okay, so there, someone says they gave you a point.
Yeah, they gave you a point. Okay, so they gave me the point, and the point is the point 0, 7, or sorry, -7. It's right here, 0, -7. And they gave me a formula for the slope, so I can find the slope if I go ahead and then substitute 0 in for t, and if I substitute -7 in for w. So my slope is going to equal 2 times 0 times -7 plus -7. Oof, that's getting kind of messy. All right, so I know that my point is 0, -7, and I know that my slope now is -7. And now I'm going to write the equation of the tangent line. So it's going to be y minus -7 is equal to, so y plus 7 is equal to my slope, -7, times x minus 0. There's my tangent line, and now I'm going to use it to make this approximation, which means I have to substitute 1 in for x or t, it doesn't really matter. So I get y plus 7 is equal to -7 times 1 minus 0. So -7 times 1 minus 0 is -7. Subtract 7 from both sides, and my approximation ends up being -14. Now, to be honest, I did not work this morning. I hope I'm right. I can check myself though. So the answer for I is -14. Oof, I'm pretty relieved. That's my approximation. But the reason I bring this up is that many times you can go ahead and work with a differential equation and never ever find the particular solution or even the general solution for it. So that would be a good example of that. All right, the next one we're going to work is going to be A. So let's go back and take a look at A. And again, if people need me to slow down or answer a question, please put it in the chat and hopefully Aaron will nudge me. Okay, nothing's in the chat right now. All right, this one, back to A. We already spent some time classifying this one. It says the velocity of a particle traveling along the x-axis is given by dx dt is equal to -2t plus 3 for t is greater than or equal to 0. If the particle begins at x equals -5 when t is equal to 0, what is the particle's position when t equals 2? There's actually two different ways to do this problem, and I'm going to do it the way that I generally do these questions unless I'm kind of stuck. It's like you can do the accumulation model this way, but I tend to try and solve the differential equation first if I can. That's just me. So I'm going to go ahead and explicitly solve for x of t and then substitute in 2. That's going to be my path. Okay, so what I mean by that is I'm going to say, all right, dx dt is equal to -2t plus 3, which means that dx is equal to -2t plus 3 dt. And now I'm going to integrate on both sides. I see some of my basics from just a couple of hours ago. The integral of -2t is going to be -t squared. The integral of 3 is going to be 3t, and then plus some constant. The integral of dx is just going to be x. That's like a 1 right there. So the antiderivative of 1 would be x. In other words, if I took the derivative of x, I would have gotten 1. So it said here x was -5 when t was 0. So I'm going to substitute -5 in for x. And lo and behold, I get -5 for my, that doesn't always happen. You got to really confirm that that ends up being your constant of integration. So my equation is going to be x equals -t squared plus 3t minus 5. And then when t is 2, I'm going to get x of 2 is equal to -2 squared plus 3 times 2 minus 5. So I have -4 plus 6 minus 5. Hope I didn't make any mistakes. I think that's a 1, so maybe -3. Let's check my answer. This was A, right? -3. Yay. Any questions yet, Aaron? Looking good?
Not yet.
Okay, okay. Let's look at C next. So we had already analyzed that one as well. So on this one, we're supposed to determine the velocity of the particle when t is equal to 3, given that when t is equal to 0, v is equal to e cubed. Oh boy, I feel a log coming on here. When I see something like e, I'm thinking, there's going to be a log in this problem probably. Okay, so let's see. I've got my differential equation. And it's not telling me to sketch a slope field or write the equation of a tangent line. So I'm just going to go straight up, start solving it. So I've got dv dt is equal to t squared v. Here goes my yellow sheets. I'm moving all this stuff. Remember, this lesson all started with me in the wrong spot. I didn't have connectivity earlier. Okay, so I'm going to go ahead and separate my variables. So I get dv divided by v is equal to t squared dt. This right here is a little confusing. I think I would rewrite it as 1 over v dv is equal to t squared dt. And then once I've separated, I can go ahead and start integrating. The integral of 1 over v dv is the natural log of the absolute value of v plus c. But when we're solving these kind of problems, I usually leave that plus c on the other side. And it doesn't really matter. A lot of times people will say c1, c2, you know, whatever, but I generally always put the plus c all the way at the end on the right-hand side. Integral of t squared dt, that's going back to our basics. So 1/3 t cubed. I'm going to move this plus c over here. That makes me annoyed when it's too far away. All right, then, okay, this is important. Everything is important, but this is especially important. I am now going to find my constant of integration by substituting in before I solve for v. So I have the natural log of the absolute value of e squared, which is the same as the natural log of e squared, and then substituting in 0 for t. I get 1/3 of 0 cubed plus c, which is 0. So 0 plus c is c. And then the natural log of e squared is 2. Bringing it full circle, no pun intended, on your yellow sheet can go things that are not necessarily calculus. We get so much better at trig and at logs and at algebra. If you need to put those on your yellow sheet, such as the natural log of e is equal to 1, the natural log of 1 is equal to 0, the natural log of e squared is equal to 2, etc., or any sort of trig stuff. Cosine of pi is -1. Anything you need to put on your yellow sheet, even if it's not officially calculus, it's your yellow sheet tailor-made by you for you. So put it on there. All right, now I've got coming back to this line, and I'm going to incorporate the fact that c is equal to 2. So the natural log of the absolute value of v is equal to 1/3 t cubed plus 2. And I need to exponentiate to try and solve for v. So I get the absolute value of v is equal to e to the, this is all up in the exponent, my goodness, it's tiny, tiny. E to the 1/3 t cubed plus 2. All that's up in the exponent. And then I need to pick a branch. I need to decide with this input-output relationship if x is equal to, or if t is equal to 0, I need v to be positive e squared. So even though when I solve, I get v is equal to plus or minus e to the 1/3 t cubed plus 2, I need to really realize that I'm going to pick the positive branch. So I'm going to slide over here, and I'm going to say v is equal to e to the 1/3 t cubed plus 2. Now, that's my solution, my particular solution, and I was asked to determine the velocity of the particle when t is equal to 3. So now I have to substitute 3 in for t. to check my answer. So I have v is equal to e to the 1/3 times 3 cubed plus 2. So 3 cubed is equal to 27, times a third is 9, 9 plus 2 is 11. I'm thinking that my answer is e to the 11 for e to the 11th power for c, and I'm going to check it. Yay, smiley face. That's right. Okay. I think we have time for one more, which is a miracle because then I will have actually done what I had planned to do. And this one takes me back to D, okay? So that we've seen kind of one of each category. And Mark and I both have had, although I know for the students this is like snore, we don't care. But Mark and I have had a lot of experience grading student work on AP exams on the free response section. And so a lot of the stuff that we write for you for practice purposes is because we see the kind of student mistakes that get made. And this is one in particular that it's very challenging for students, I think, to correctly solve this differential equation to find this particular solution when only the dependent variable is showing. So many of you put into the chat that only the dependent variable was showing, and you are correct about that. But in this case, like I said, it is a challenging maneuver, I think, to solve. So let's go ahead and give it a shot. Y prime is equal to 2 root 3y minus 1. In fact, instead of y prime, I think I'm going to be better off seeing the differentials. So dy dx is equal to 2 square root of 3y minus 1. This dx needs to get over here with the x's, of which there are none. And this root 3y minus 1 needs to come to the other side. Okay. So there's a couple of different ways to do it. But I tend to leave my coefficient over there. So I would say 2 dx, and then divide both sides by this square root. So I have dy divided by 3y minus 1 equals 2 dx. Now, because of the way the square root function behaves when you anti-differentiate, you might actually want to have the 2 over here, but for most situations, if there's a coefficient, I'm going to advise my students to leave it with the dx. Okay. Now it's time to anti-differentiate. And before I really do, I'm going to write my integral symbol, and I'm going to say 3y minus 1 to the negative 1/2 dy is equal to the integral of 2 dx. And the reason I'm going to do that is that now this kind of looks like a power function. In fact, I can go back to my handout from earlier. Well, I guess I didn't have a square root in the denominator, even better. So this negative 1/2, I'm going to add 1 to my exponent and divide by my new exponent or multiply by the reciprocal. But unfortunately, not unfortunately, I don't mean that in an unfortunately way, but this is a little bit more complicated than just x to the 1/2 or y to the 1/2. So I really need to think about the fact that I need to do some sort of a rewriting of this integral here. If u is equal to 3y minus 1, then du dy is equal to 3. So du divided by 3 is equal to dy. And I can put du divided by 3 in right here. And I can rewrite this as u to the negative 1/2. So that's what I'm going to do. I'm going to say the integral of u to the negative 1/2 and then times du over 3. With this 3 really being a 1/3 out front. So I have 1/3 u to the negative 1/2 du. Now, really what I'm doing here is I'm kind of like going all the way off-road to kind of get back to where I can solve this differential equation. I'm going to do just one more step, and that is I'm going to anti-differentiate in here. So I get 1/3 u to the positive 1/2, because negative 1/2 plus 1 is positive 1/2. Divide by the 1/2. That's the same as multiplying by 2. And then I get my plus c because I'm just in the habit of writing that. So what does that mean for this problem? What that means for this problem is that the antiderivative here of 3y minus 1 to the negative 1/2 is actually 2/3, and then in parentheses 3y minus 1 to the positive 1/2, replacing that 3y minus 1 into where the u was. And now this is going to equal 2x, that's the antiderivative of 2, plus c. So there's my, I've got my face over that, but you guys hopefully can see it. There's my, this is all that side work. There's my next step after taking the integral of both sides. Again, I find better success if I plug in my initial condition and then find my c value and then rewrite. So f of 0 is 37/3. So that seems like a weird initial condition, but as soon as I start substituting it in, 37/3 times 3 is going to work out quite nicely. And then 2 times 0 is 0. So let's see what happens. 37/3 times 3 is 37. 37 minus 1 is 36. 36 to the 1/2 is 6. 2 times 0 is 0 plus c. So I have 2/3 times 6 plus c. 3 goes into 6 2 times. 2 times 2 is 4. That's how I was taught it a million years ago. And it's still stuck with me. All right, so I have 2/3 and then in parentheses, 3y minus 1, close parentheses to the 1/2 equals 2x plus 4. Now, I have to find the particular solution, so I still have to solve for y. So I'm going to multiply both sides by this reciprocal, then I'm going to square both sides, then I'm going to add 1 and then divide by 3. So I'm going to get 3y minus 1 to the 1/2 equals multiplying both sides by this 3/2. It's going to be 3/2 times 2x plus 4. Aaron, if there's something in the chat, let me know. I feel like somebody just put something in the chat.
They're just commenting on your pens.
Oh, friction. Yeah, I'll talk about those in a minute. Squaring both sides, I get 3x minus 1 is equal to 3/2 times 2x plus 4 to the squared power. And then I'm going to come over here and I'm going to add 1 to both sides and divide both sides by 3. So it's going to be y equals 2/3 and then 2x plus 4 close parentheses squared plus 1 all divided by 3. I didn't have to pick a branch here because squaring both sides just yields one answer. It's when you have absolute value or when you take the square root of both sides that plus or minus pops up. Okay, now I have to evaluate f of 1. F of 1. So let's see here. I'm going to put a 1 in for x. So I'm going to have 2/3 times 2 plus 4 quantity squared plus 1. If there's anybody out there noticing I'm making a mistake, I hope you yell at me. All right, so 2 plus 4 is 8. 8 times 2 is 16. Divided by 3 is, my goodness, 16/3 squared plus 1 all over 3. I'm going to check my answer to make sure I don't have any sort of crazy stuff. So my answer says 82/3. And of course, on the free response, we could leave it like that, but I'm really nervous that this is not correct. So I'm going to just check it for myself. Okay, so I've got 16/3 and then squared and then plus 1 and then divided by 3 and then change it to a fraction. Yeah, that's not right. Where's my mistake?
When you did 2 plus, it was 2 plus 4 is 6.
Ah, my gosh, that's crazy. Now you can really see my erasable pens. 2 plus 4 is 6. 6 times 2 is 12 divided by 3 is 4, right? So is that right?
Let's see, other comments. The coefficient should be 3/2.
Oh, jeepers. When I brought it over here, it was 3/2. Sheesh. Okay. So then this wouldn't be a 4. So we're getting closer. We're getting closer. 2 plus 4 is 6. This would be 9 squared. 9 squared. So this is 82/3. Thank you for all of your help, everybody. Oh my goodness, it takes a village. Yikes. All right. that's a good example of you can get tired after 2 hours of doing this. So that's going to happen to you on the AP exam as well. You just got to kind of reboot, I guess, so to speak. Okay. So any other questions or comments that you guys have before we say goodbye?
None are showing up. All right.
Well, yeah. Well, I'll just, as people are kind of signing off and going off to whatever they're doing next, thank you guys so much for having me. It's been fun. It was fun to think about what to share with you guys, and maybe I overshared. That happens. I can't just do a little bit of stuff. I got to kind of give you some stuff to chew on for yourself. So make sure to reach out if you're stuck on anything and you want some feedback, especially on those Desmos activities, or on the circuit, or on the sort and solve for the differential equations.
Yeah. And I've got the screen up now. So if you need to email Virge because you want to check your answers for her first Desmos activity, her email is there. And then the links to the recordings are also posted.
This is for William Freeman. He says, what about inverse trig functions at arctan or arcsine? So in calculus, for arctangent and arcsine, when you're going, so the derivative of inverse cosine is going to be the opposite of inverse sine. So if you've got one memorized, you've kind of got both of them memorized. And then I wish Mark were here to back me up on this, but I'm pretty sure that like inverse secant and cosecant really are not tested very much on the AP AB exam anyway. Inverse cotangent, of course, is just the opposite of inverse tangent. So if you get on your yellow sheet, if on your yellow sheet you want to put all of those other ones on there, especially for next year to have them when you're at a higher level, then you definitely should, to help you study. But they just don't show up that much in terms of bang for your buck.
All right. So if there are any other questions, go ahead and put those in the chat.
Yeah,
here.
I can definitely stay on.
Otherwise, yeah, the link to the recording of today's session will be posted sometime this weekend. And then please come back next week. It's right before the first administration of the AP exam. Dixie Ross joins us for integration applications area and volume. So that should be a treat as well. So
yeah.
Thank you, Virge. I know everybody is giving you their thanks in the chat, so we certainly appreciate it.
Thanks for inviting me, Aaron.
Yeah, at any time. You know, we are happy to have you all to work with.
All
right. So if that's all, then everyone else, you all have a good rest of the day, and hopefully we will see you back next week.
I'm going to sign off then too. Okay, Aaron?